Hi, I'm Alistair, I'm a games designer, and normally in this channel I would describe how to create games suitable for use in an escape room. Now, given what's going on in the world at the moment, escape rooms are closed, but escape room owners have been very innovative and creative in coming up with new sorts of games that allow players to continue to enjoy them even during lockdown. And that's what's inspired me to make this video. So some people have been creating online versions of their escape rooms that you can play through a web browser. And that's fine, and it continues to give you that kind of puzzle hit, but it feels more like you're playing a video game. You lose that kind of tactile interaction and puzzles that are based on physical manipulation of real objects. It's not quite the same when you get a little message pop up in your web browser that says, "Congratulations, the lock has been unlocked," or whatever, compared to actually seeing a cupboard door physically pop open in front of you. Now, some other escape rooms have been using a kind of remote playthrough alternative. So this is where there is a real-life person, normally an employee of the escape room, and they are physically located in the normal room that you would play through, and they have a GoPro camera strapped to their chest, for example. And the players remotely get to see a video stream of what that person can see, and they give commands for that player to carry out inside the room. So they're kind of acting like an avatar for the players, basically, and you get to solve all the normal puzzles that you would do in the normal escape room game, but it's all being kind of mediated through this other person that you're giving commands to. Now, what I wondered is if there is some way to combine the best bits of both these two options, given the restrictions that we have to have players operating remotely. Could we still give them that feeling of agency, that they are the ones making these actions, making these events happen, and also somehow relate that to interacting with physical objects in the room rather than everything just appearing on a computer screen? And in fact, I wanted to go one step further than that still. Given that escape rooms are not just about solving a series of puzzles, they're actually an immersive experience. Is there a way that we could actually make use of the opportunities of this narrative, a reason why the players are operating remotely? Can we tie that into a story and a narrative and actually make it part of the experience itself, rather than thinking of it as a limiting factor, actually treat it as an opportunity? So here's what I came up with. Imagine a bank heist or a covert spy operation. These are already genres that are popular in many common escape room games. Now, if you think about a film or a TV show that uses one of those settings, you don't have the whole criminal gang enter the bank to steal the diamond, though. You have one guy, the man on the inside. He's the one that rappelled down from the roof and, is going to grab the swag and put it in the bag. The rest of the criminal gang, they're all waiting in the black van outside. And you've got the different roles to play in that criminal team. You've got the nerdy computer one who hacks into the mainframe and disables the security system. You've got the girl that's listening in on the radio for incoming police messages and can warn them when a security guard's about to come around the corner. And you've got the kind of the head of the gang. He's the one that's calling all the shots and deciding what actions people should take. And I think if I were to structure an escape room game in this kind of world at the moment, this is how I would position it. So the remote avatar person, the person with the GoPro camera on their tummy, don't think of them as a GM or an avatar. Think of them as a member of the team. He's the guy on the inside. And that gives you the reason why he is being given instructions on what to do. I mean, he's the muscle of the gang. He's not the brains, though. The brains is everyone that is outside in the black van, and that's your remote team players. That can explain the situation, it gives them the motivation, and it kind of sets everything up for the way they're going to interact for the rest of the game. So that can provide a narrative explanation of how come players find themselves operating remotely in this game. Now let's look at the other side of the problem, which is how do we give them an experience that lets them feel that they are able to directly interact and modify the physical environment in which the guy on the inside finds themselves, even when they are only able to access it remotely. So to do that, let's take an example of one of those roles in the gang, that of the hacker, the person that's going to break into the mainframe system, disable the security, and allow the character on the inside to be able to access a new part of the room. Now, most escape room games control access to areas using maglocks like this. And they are often in turn controlled by puzzle controllers run by microprocessors, like this Arduino. So in this video, what I want to do is to explain how we can expose the behavior of an Arduino like this over the internet, so that players remotely on the other side of the world or wherever they might be playing through this game can effectively log on and control the behavior of this Arduino to release the maglock, allowing the on-site player to progress through the room. Okay, so now what I want you to imagine is that I am the guy on the inside. I'm the person that is physically in the escape room. I've been going around, players have been telling me what to do, I've been solving puzzles and getting items. But now I've got stuck here at this security door. Now, what you can see above me here, obviously, is the Arduino with the Ethernet attachment to it. It's securing this maglock, and let's say that this maglock is holding the door closed. Obviously, it's actually not at the moment, but I want you to see what's going on. Now, me as the player in the room, I'm a little bit simple, and I don't really know how to get past this. I need the other guys on my team to help. I need the players to solve the problems to open this door for me. But the only things I've got to help them are some scraps of paper that I picked up as I was going round. So I've found this, which just says online security system. Don't know what that means. And I've also found this here, which is the security override password. Again, I don't know what that means. I'm just the brawn, I'm not the brains of the operation. But maybe there's something that the players can do remotely that means that I'm going to be able to get through this security door in front of me. Okay, so your team of remote players have been watching the progress of our man on the inside through a video stream, through Skype or Zoom or whatever application you want. And fortunately, they're a little bit smarter than the guy on the inside. And they've realised that in order to deactivate the security door, what they need to do is to log on to that security server that they found the IP address of in the room. So what they can do is they can actually load a web browser on their computer, and having done that, if they go to the IP address that the player in the room found, what they'll do is they'll be served up a web page like this. Now this is just straightforward HTML that was defined on the Arduino in the room itself. We're connecting directly across the internet to that Arduino. We've been sent this code, and I've just put some simple styling on it here, but you could really theme this however you want. And we're prompted to enter a security code. Well, we found that in the room as well. Now, I just chose a simple 4-digit code, 1234, because escape room players are familiar with finding 4-digit codes. Normally they enter combination locks. But this could be a word. Maybe this itself would have to be derived from another puzzle, so you could kind of add another layer to this. And when you submit this, we find that the door in the room opens and our guy on the inside can actually progress through and we get onto the next part of the room. Now, obviously, one of the other things about the current climate is that it is a little bit harder than usual to get hold of electronic components. And the other thing is that for escape room owners who have been forced to close their rooms, they're obviously desperate to get games up and running quickly so that they've got some sort of cash flow coming in. So with both of those in mind, I'm going to try and demonstrate a whole range of different hardware and different methods you can use to achieve this same objective. So hopefully whatever you've got available or whatever you can get your hands on, you'll be able to implement a version of this particular kind of puzzle type. So to start with here, I've got an Arduino Uno and it's got an Ethernet shield stacked on top of it. So this particular shield uses something called a WizNet W5100 chip. There are newer versions of that chip as well. There's the 5200 and the 5500, which offer a few extra features, but it will work fine on the 5100 board. And that's a very solid option. If you're already using Arduino Unos to control your props, you can simply plop the shield on the top of it. Here's another option if you want a wired network connection. So here I've got an Arduino Nano, and this is going to a different type of board. This is called an ENC28J60 board. Again, it gives you an Ethernet port that you can plug into your local network, and from there you can expose it to the internet to control a maglock from the Nano. So they're two wired options. You can also get wireless options as well. So here I've got a Nano that's plugged into an ESP01 board. The ESP01 itself is actually a kind of ESP8266 board, but this one here I'm using just for its Wi-Fi functionality. The game code itself is running on the Nano. I've also got a standalone ESP8266 board, and I've also got an ESP32 board. So I'm going to show you the wiring and the code for all of these different boards, so whichever ones you've either already got or can get your hands on, you'll be able to implement this particular type of puzzle. Let me show you how it's going to work. So I wanted to show the wiring diagrams for all of the possible boards in one place. Partly because, like I said, I don't know what boards you're going to be able to get your hands on or already have available. So I wanted to kind of provide as much of a thorough overview as I could. And secondly, because it'll actually let me make a bit of a comparison between the options. If you do have a choice available, they don't all work in exactly the same way, and there's some that you might prefer over others. So at the top of the screen here, I've got my options for the wired connection, and at the bottom here I've got some options if you wanted a Wi-Fi connection instead. In both of these cases, this would connect to your local router gateway first, and from there you would expose it onto the internet for players to be able to control. So let's sort of have a look at each of them in turn. So starting off at the top corner here, we've got the W5100 Ethernet shield. So this, if you are already using Arduino Unos in your room anywhere, this is probably the easiest solution for you. The board itself here just slots on top of your Uno, and connections are made to all the relevant pins it needs to work. So those are, it's an SPI connection, so it connects to pins 10, 11, 12 and 13, to ground and to 5 volt as well, but it also makes all the other GPIO pins available on the top as well. So it's a very convenient board to use, it's very easy. And it's pretty reliable, and it's got some nice LEDs on it and things that show when data is being transmitted and received, or when a connection is made, things like that. The only disadvantage I'd say of this is that the design of the board itself, rather like the Uno, is a little bit dated now. So it's probably, 7 years old or something like that probably. And there are perhaps newer, more advanced chips available. So speaking of which, the next option here I've got. So this is an alternative way of packaging up one of the WizNet chips. So the same chip that you get in the Ethernet shield here, you can get in a kind of breakout module form, and that's what I've got here. But that's the W5100, but you can also get the newer chips, the 5200 and the 5500 as well. They work in the same way, they have the same connections and use the same libraries. They've just got slightly more features, they're a little bit more advanced. And the advantage of getting them in a package like this is that this is kind of a generic breakout board. It's not structured to fit an Uno particularly, although I'm showing an Uno here. You could use a Nano or a Mega or any other microprocessor that has an SPI connection, and then you would actually just, rather than the shield option here where you just kind of slot it onto the GPIO pins, here you explicitly create the connections between your Arduino pins 10, 11, 12 and 13, the reset, ground and 5 volts on this line, to the corresponding pins on the breakout module here. And again, that then gives you an Ethernet connection that you can plug your cable into, your Cat5 cable, into there. So these hardware-wise are very similar. This one is specifically for an Uno. This one is for any microprocessor. You have to do the wiring yourself, but you can get slightly newer chips in this format. And then my third wired option, this is a different design because this uses a different chip from a different manufacturer. So this is the ENC28J60. And like with the WizNet chips here, it uses an SPI interface still. So again, you use Arduino's pin 10, 11, 12, 13, reset and ground. The difference in this module is the way that the power is supplied, however. So the chip here, the central ENC chip, runs at 3.3 volts. Now it's 5 volt tolerant, as what we say. So these SPI connections here, they can go straight to a 5 volt Arduino. That's okay. The problem comes with the VCC supply itself. So on some breakout boards, they have a voltage regulator on the board, which means that you can supply 5 volts, as I have done here, into the VCC input, and it will be regulated down to the 3.3 volts required by the processor. On other boards, however, though, that voltage regulator is not present, and you actually need to supply 3.3 volt input instead. Now you might be thinking, well, that's not a problem because Arduinos have got a 3.3 volt out here, so why can't we just take the VCC and wire it into that port instead? Well, the problem with that comes from the current draw of the chip here. So it turns out that transferring data over an Ethernet connection is actually fairly power intensive. And when you are connecting, when you're actually transferring data over an Ethernet using a board like this little board can draw around 180 milliamps or 200 milliamps in that kind of area. The 3.3 voltage regulator on the Arduino, however, can only do 150 milliamps. So you can't use the 3.3 output if you've got a board that needs a 3.3 input. What you're going to have to do instead is get an external 3.3 voltage regulator. Or you could take the 5 volt out here and run it through a voltage divider or like an AMS 1117 regulator or something like that to a 3.3 input. But that's all kind of extra faff, extra components you need. So if you're getting a board like this one, I would encourage you to get one that runs at with a 5 volt VCC input if you're going to use it with a 5 volt Arduino. This board I personally find a better choice to use. I found it a bit more reliable, a bit more faster as well, and it has the advantage that, like I say, you can plug it into anything that has an SPI interface, although it's probably the most expensive of the wired options. The Ethernet Shield has been around for a while, it's pretty robust, it's well used, and if you're already using an Uno, this is a very good choice, but it's kind of limited in its design to really only be used with that particular board underneath it. Okay, so those are your wired options. Let's take a look at the wireless options. So the first one I'm looking at here is something called an ESP01. And this is a kind of an add-on board, just like the ones at the top, just all like the wired connections needed an existing Arduino to plug into. This is kind of like an add-on board as well. And rather like the ENC28J60, this is a little bit complicated by virtue of the fact that it too runs at 3.3 volts. So what we've got here is we've got a send and a transmit line. That's the yellow and green here. So the transmit from the Arduino, we're having to create a voltage divider. So I've got a 1 kilo ohm resistor here, a 2 kilo ohm resistor here. So that's going to take a third off my 5 volt output from the Arduino and send that to the receive of the ESP. Coming back, the transmit of the ESP, that's at 3.3 volts, so I can plug that straight into a 5 volt input on my Arduino. So that's okay, I don't need resistors there. But I've also got to plug in the 3.3 volt power supply coming to the bottom here, and also to the enable pin, and that's got to go through a 10 kilo ohm resistor on the way in. So this is all a little bit of a fiddly bit. You'll need extra components again. However, you can get an ESP01 adapter board. That looks like this. It's just a little extra shield that fits underneath, and this simplifies the wiring a lot. When you use one of these, basically what it does is these little components at the edge here provide what I've had to manually specify there in the code. So now you can plug it straight into 5 volts, that should be at the bottom there, and ground, and also to straight into your GPIO ports here to the transmit and receive. It will cope with all of the logic level reduction and the voltage regulation here to the board. So that's, if you're going to use an ESP01, I strongly encourage you to use an adapter for it because it will make your wiring simpler. However, there's still problems here. Effectively, your main program code is running on the Arduino at the bottom, or your network connection is running on the ESP at the top. But the interface between them, we're just using a serial connection. So unlike the examples at the top where I had an SPI connection, here we've got a serial connection, and that's normally pretty slow. If you're using software emulation on serial ports like this, you typically run it at 9600 baud. That is going to be quite sluggish to serve up a web page for your players, and when they do some input on the interface here over the web, it's going to be slow to respond. So although this simplifies the wiring, it actually doesn't fix the problem of speed, really. For that, I would recommend one of these two options at the bottom. So these are not technically Arduinos, in that they're not manufactured by Arduino, and they don't use the AT mega chips. These are the ESP8266, and then the newer version of that, really, which is the ESP32. These are using chips manufactured by a company called Espressif, and they are essentially kind of super powerful Arduinos. You can still program them using the Arduino IDE. You can still use many of the same libraries that you're used to using, and you have, you know, your range of digital and analog output pins here that you can address. They have a slightly different form factor, they look slightly different, and there's a few kind of odd quirks to get used to. So like on the ESP32, when you actually want to upload new code to it, you've got to hold down one of these buttons on the board here while you upload new code. But they are super powerful, and more to the point, they have Wi-Fi built into the boards themselves. So unlike all of the previous examples here that you've had to add some extra components onto there, with these two boards here, you can actually be running your main program code itself. You can be attaching buttons or LEDs or LCDs or maglocks or whatever you want to all these buttons here, and also you've got the benefit of inbuilt Wi-Fi with no extra hardware. If you're using the ESP32, you've also got Bluetooth, you've got a real-time clock, you've got capacitive touch sensor inputs on some of these pins. So this is, you know, really quite a very capable little board. It is probably the most expensive option of the ones that I've got here. And, you know, if you're not currently using them, I don't know what availability will be like. I normally get mine shipped from China, and they take kind of 2 weeks to get here to the UK. But given the current situation, obviously you might expect that to be slightly longer. So I'm going to kind of leave it here, but keep you with the other options. So all of these will essentially provide the same functionality that you're looking for. If it were me, for a wired option, I would probably choose this one at the top, and for wireless, I would go for the ESP32. But if for whatever reason you can't get hold of those, or you already have some of the other things available, and then that is how you would connect them and use them. Now, in terms of the code, again, there's differences depending on which of the particular hardware options you're using. and also whether you're running on an Arduino or one of the ESP devices. But there's quite a lot that they have in common. I've tried to follow the same approach in all of those devices. So I'm going to talk through this particular example code. This is the one designed to run on the W5100 Ethernet shield on Arduino. But this is very similar to any of the other examples based on the Arduinos. Then I'll talk through the example on the ESP later, because that's slightly different. Okay, so we start off with including the libraries we're going to use. If you're using the W5100 or the WizNet modules, you'll use this library here, Ethernet. This is built into Arduino. If you're going to use the ENC28J60, you use an alternative library called UIP Ethernet, but other than that, basically retains exactly the same other functions. And if you're wanting to use the Wi-Fi ESP01 option with an Arduino, you'd replace this with the Wi-Fi ESP library. Those are all available for free. Like I say, this one comes with Arduino anyway. UIP Ethernet and Wi-Fi ESP are available on GitHub, and I'll put links in the code for those to get them. So that kind of provides all the functionality of doing the networking, transferring and retrieving data. I'm also including an extra local library called ring buffer, and I've got that defined up here. So this version of it came from the Wi-Fi ESP library, but actually it's a very generic function. And a ring buffer is a temporary store of data. You can think of it a little bit kind of like a running total kind of thing. It keeps a certain amount of data, and then when you try to push any more data to it than it can hold, rather than just rejecting that data or kind of filling up or giving an error message, it basically just keeps the most recent X bytes, so 8 bytes or 16 bytes, however many you want, and then it continually overwrites the oldest item from the buffer with that new item of data. So you can imagine it like a ring going round and round. And we're going to use that to analyze the request that comes in from a web browser over the internet, and to work out things like what web page was being requested, or if they filled in a form, what values they filled in the form. Now, if you were writing a web server that was running on a more powerful device like a PC or a dedicated web server, you'd want to analyze that whole message for everything they requested and kind of treat it as one. But because we're only dealing with very small devices here that don't have much memory, we're just going to hang on to a small amount of the most recent data and just analyze it kind of a chunk at a time, just to pull out those bits that are important to us. And to do that, we're going to use this idea of a ring buffer. So those are the libraries I'm using. Then we go on to the constants. So these are the sections which are going to remain the same throughout the duration of the code. If you're using the W5100 device or the ENC device, you need to assign a MAC address in code. So a MAC address is a unique address that identifies a piece of hardware on a network. Now, some devices, and in fact, in a sense, the way that this should happen is to have a MAC address assigned by the manufacturer. So a manufacturer will have a particular code that is their manufacturer code at the beginning, and then they just have an incremental code at the end that they'll add on for every new device they create. But if you're using some of these shields, you'll find that the manufacturer didn't actually assign a MAC address to the device, so you need to do it yourself. And essentially the only rules here is that it's got to be a 6-byte code that is unique on your network. Now, in an ideal world, it would be unique on the complete internet, but actually that doesn't matter. So long as it's unique on your local intranet as far as your router, once we get beyond that onto the wider public internet, we're going to be routing all information through that single gateway anyway, and that can assign it to a local MAC address. So this just needs to be, you can set any value you want, so long as it's these hex values within the range here. So I've just done A, B, C, D, E, F, and then for however many devices I have on my local network, I I do 0001, 02, 03, that will be plenty enough uniqueness on your network. I'm also going to choose an IP address, so a static IP address, which this device is going to request from my local router. Again, some routers will use DHCP to assign an IP address. So, rather than the client specifying I would like to be at 192.168.141, you can just say, give me the next freest IP address. That's going to make it more difficult later on for you, though, because we're going to be trying to route data to this device. And it's much easier to do that if you definitely know that it's had a static IP address assigned each time. So I'll show you that the network configuration of my router and how to open ports and things a bit later on. But for now, again, I'm just assigning an IP address that I know is in a range that my router can assign. And I'm choosing a port that this service is going to run on. Now, web servers normally run on port 80. That's the standard port for HTTP traffic. But I guess partly to aid in kind of obscurity. I don't want people to accidentally find my Arduino on the internet somewhere and be sewing up this thing. So I've chosen a slightly more obscure port. When the user has to go to this web page in their browser, what they type is they type the IP address that they want to go to. So let's say it's 192.168.141. It won't be that, actually. It will be the wide area network address. And then they type the port number after the colon there. Now, that would be what you type if you wanted to access this device from your local intranet. So any of your other devices on your network, in your within your escape room network. What we're actually going to do is we're going to get a wide area network instead. So what we're going to replace this bit here is going to be the IP address of our gateway to the wider internet, and maybe that's something like that. But we'll keep that port number the same, and what we'll tell our gateway to do is to route any incoming traffic on that port to this device. In fact, we'll do it by the MAC address here. But so that's how it's going to work. We're going to say this will be, that's your wide area network address for the gateway of your network. So the point where it goes through your internet router, this is the IP address that's assigned by your internet provider. And that's the same for every device on your network, because generally speaking, the public internet can't access individual devices on your network. But when a request comes in on this particular port here, we're going to route it through to this device. That's how we're going to use that there. Okay, and compared to that, this will seem nice and simple. So we're going to have a relay connected to one of the GPIO pins, and we're going to use pin 7 in this case. Okay, then we go on to the global section. So having included the library for that ring buffer, let's actually initialize it now. And I'm going to use a 16 byte ring buffer there that's just going to roll round and round and carry 16 characters and HTTP request that we can analyze and see what's going on. And we'll actually declare our server object as well and the port on which it's going to listen to. Then we go into setup. So we'll start a serial connection. That's not required, strictly speaking, but that will just help us to see the information of what's going on when we look at it locally to see whether any clients connect or anything. That will come up in the serial monitor for the Arduino. We'll start our Ethernet connection using the requested MAC for the hardware and asking for the requested IP address as well. And assuming that gets assigned, what we'll do is we'll dump some information out to the serial monitor to say the IP address that we're using. We'll start the web server then. So this is about connecting to the network, this bit. This next section is about actually starting the server off on the local device. And we specified the port that was going to use up here already. We'll initialize the output pin that we're going to use. And finally, we'll just put a little bit of delay just to make sure that everything is kind of stabilized and set up before we go into the main program loop. And this is the main program loop. So it's actually, it's not that complicated actually. The vast majority of it is this bit here, which is actually feeding the HTML of the web page back to the client. So we'll just step through it again. And on every iteration through the loop, so we've got our server running now. What we need to know is, have any clients connected to our device? So has anyone from the internet loaded their web browser and requested a response from this port of our IP address? So that's what this server available does. It tells us that there is a client that has connected, basically. So if that's true, there is a client. What we're then going to do is we're going to initialize our ring buffer. So that's going to clear it out of any old data that might be there left over from last time. And then for as long as that client is connected, and so long as they have requested something from this device. So in practice, what that means is they've requested a web page, or they've submitted a form. Something in their browser has requested a response from this device. What we're going to do is we're going to read the contents of that request, and we'll just output it to the serial monitor just so we can debug what's going on. But more importantly, we'll push it onto our ring buffer. So this is our rolling buffer of information about what this user has requested from our device. And what we're then going to do is we're going to continually examine what is in the buffer to see to work out how we're going to respond accordingly. Now for these bits here, you might need to know a little bit about how HTTP works generally. When you go to a website, let's say you go to I don't know, the BBC website here in the UK. So if you go to www.bbc.co.uk/news, let's say, what actually happens there is that request, the first part of that, the website name, the bbc.co.uk, that gets translated through a DNS lookup into the IP address of the server. So that tells you which server you're going to go to. And then the /news bit at the end, that's what's called a GET request. It says the name of the resource on that BBC server that the browser wants to see. And when that gets received by the web server at the BBC end, this is what that looks like. So if you were going to go to the news page, let's say, that request would actually be received by the BBC server looking something like that. But in our case, we're not going to serve news from the BBC site. What we're going to do is we're going to have two web pages, essentially, one of which is just going to be called H, and one of which is going to be called L. And unsurprisingly enough, they are going to turn our relay pin high or low. Okay? So when we find out the website address that we want to go to, if we add a /H to the end, that's going to activate our relay. If we add a /L, that's going to deactivate it again. Okay, so that's nice and easy, and you could put those links as hypertext links on a website and just go to them, and they would turn the relay on or off. But what about if you wanted to make it a bit more complicated? Rather than having a hypertext link to one of those pages, what if you wanted to have a form that the user entered the correct value into before activating the relay? Well, that's what this next example shows us. So this time we're going to look in the buffer, and we're going to see if the page requested has this slightly peculiar !P = 1, 2, 3, 4. So the question mark there shows that these were parameters that were supplied as part of the GET request. So this is kind of like a fixed resource, the L and the H, they're like our web pages. This is parameters that were supplied in a form, and the form had a variable that was called P, so for password in this case, and the value for that variable or that parameter was 1, 2, 3, 4. Now this is going to be generated by our form that we've got in a moment, but what we're going to do in this case, so when that happens, when the user submits a GET request and what they're getting is a resource that corresponds to p equals 1234. Well, we're going to use that as our password. And when you enter the password, we're going to set the relay high for half a second, then we're going to set it low again, and we're going to put this text on for correct password entered. So the assumption is that these two here, these are kind of links that the user could follow directly on the page, or they could be told and no to these links. This one here, this is more of like a dynamic kind of input that they have entered that has taken them to this series of actions here. Okay, so that's all of the kind of responses that we need to create to specific actions that users' browsers have requested. But what we haven't actually done yet is sent them a web page on which they can enter these actions. So that's what the next bit does. So if in our buffer at some point we see this pattern here, what this is a carriage return followed by a new line, and in fact it's two of them in a row. So it's carriage return, new line, carriage return, new line. That is how all web browsers kind of sign off the end of their requests to a web server. So you get a complete blank line at the end of the HTTP request as it is. So you've said we filled in this web page and we want this resource from the server, or we've entered a form, we've entered this value. When we see this bit, that means that we know we've got to the end of the request. There might have been other stuff in the meantime. And in fact, you do get a load of extra metadata about things like what browser the user is using and what cookies they might have set and when the last time security certificates were updated, all these things. We're going to ignore all that. We're just going to act on these bits here and this bit here. So when we get to this, we know that the request has ended. So this is the bit where we actually present the web page to the client. And again, if you know any HTML, if you've done any kind of web page design or things like that, this might look familiar to you. And we start off with this section at the top. So this is kind of like the metadata response to the browser to say, okay, we've received your request. We're going to send you a response back that's going to be some HTML. And then we'd like to close the connection after that. And then this bit here is actually the HTML of the page they receive. So it's a very basic page I've put here. We're going to put a header at the top that just says escape room controller. Then we're going to create a form which has got a single text input in it. That's going to be 4 characters long. That's what this 4 is here. And we're going to give it the name P. Now this bit's important because you can have as many different types of input in your form as you want. So you could have radio buttons, checkboxes, drop downs, password entry fields, whatever. But when we see that form get submitted, it's the name assigned to each of those items that's going to appear here. So this question mark P equals 1234 lets us know that someone submitted this form with a value 1234 of this P field here. That's where it came from. We have a submit button as well. That's not going to give us any value here, but it's just going to actually act on the form being submitted to send this to the server. And I've also got, like I say, we've just got these examples of hyperlinks to go to the static pages. So I've got my H and my L page here. And that is what's going to generate these requests here. So my form's a bit more of a complicated example because this has a dynamic value. These ones here, these are just static links. We'll send that all back to the client, and we do that by doing this kind of client.print. That may seem slightly strange syntax, but it makes sense really. Normally we'd print to a serial connection, like here, and that's how we send data to be displayed on the IDE serial monitor. Here we're printing data back to the web browser client instead, so whatever our players have used to connect to our device, we're going to print to that connection instead. And then finally, we'll just wait a short while just after that data has been sent. We will stop the connection and we will just say that it's been disconnected. And that is it. So it's just over 100 lines, which is actually not too bad. And like I say, this example here is very similar if you're using any of the Arduino based solutions here. So the W5100, the ENC28J60 or the ESP01 all have very, very similar code logic here. And this is the code that you'd use if you were using one of the ESP chips instead, so either the 8266 or the ESP32. And in fact, you can use this exact same code for either of those devices. There are a few subtle differences between the two, but I've included them in the same code listing and just put this conditional code blocks here instead. So right at the top, for example, if you're using an ESP32 chip, you want to include these three libraries. If you're using an ESP8266, you need to include the versions of the libraries that have this prefix instead. So they have exactly the same functionality, it's just their customized versions of the library for that particular chip type. And so I've just included that in conditional statements at the top, meaning that you can use exactly the same code for both devices. And then when you come to actually compile it, if you choose one of these ESP boards like this, or if you're targeting one of the ESP32 boards here, it will include the correct appropriate libraries based on the board that you're targeting. Now, because these are both Wi-Fi devices, when we come down to the constant section, rather than specifying as we did with the wired devices, we specified a MAC address and an IP address to request. Here we're going to specify the name of the Wi-Fi network that we want to join, so the SSID of the local Wi-Fi network, and also the password needed to join that network. As before, we're also going to specify the port on which we want to run the web server on this device, so that when we get an incoming request from a player's browser somewhere on the internet, that we can route it appropriately to this device. And again, we'll use a particular pin to turn a relay on and off when an incoming request happens. When we go to the global section here, again, depending on which device type we're targeting, we have to use a slightly different named object. But other than that, these both do the same thing. We're starting a new web server listening on the port that we specified at the top. And then we go to the setup section. So we'll begin a serial connection at the baud rate specified just to display some debug information. And then we'll start our Wi-Fi connection. So ESP actually can operate its Wi-Fi capabilities in different modes. It can operate as an access point or as a station, or as both, in fact. And that's a little bit like operating as a client or a server. You can think of that as, I guess. So in this case, we want to operate as a station because we're going to be a client connecting to an existing Wi-Fi network rather than trying to broadcast as a hotspot a new network. So we'll start at the station. We'll begin our Wi-Fi connection using the credentials we specified at the top, and then we will just enter a little loop while we wait for that Wi-Fi to become successfully connected. So that will just loop round and around until we get a status update. And then again, we'll print out some debug information. So we'll print out the name of the Wi-Fi network, the IP address that we got assigned, and also the MAC address of the hardware that we're using in this device. We might find that useful in a moment when we come to configure our gateway, because a lot of that is done by MAC address rather than by IP. Now, this section here, this technically speaking is not actually required. At the top here, in the libraries, I also included Wi-Fi client. Now, most of the functionality of what we're doing here is not as a client, it's as a server. But sometimes it's useful to kind of establish whether we have internet connectivity working successfully by trying to connect to another website on the public internet. And also, it's useful to know how our device appears to the public internet, and particularly what the IP address of it is. So this is a service, this is a website here. You can go to this in any normal browser. Just go to ident.me, and what it will tell you is the IP address of your device as can be seen from the public internet. And that's going to be the IP address that we're going to need players to enter in their browser to be able to control our relay pins here. So we could have got this in other ways, essentially, but it's a useful kind of feature, I think, to demonstrate how you would do it on the device itself. So this HTTP client, so rather than acting as a server now, we're going to create a client, so a little bit like a tiny web browser running on our ESP device. We're going to connect to this service, and we're going to make a GET request. So just as players have been making to us, we're now going to make that same sort of request to another service. And assuming we get a successful response, so if the HTTP code is greater than 0, we'll read in whatever the reply was to our request, and we'll print that to the serial connection. So that's going to tell us what the IP address of our device is as seen from the wider internet. So it's our WAN address rather than our LAN address. So that bit's a bit different. The next bit is slightly different as well. So this is in a sense the main difference in the structure of this code. You remember with the Arduino examples, what I did was to create a ring buffer and to scan through that buffer for particular syntax, so for which request was being, a get /L or a get $P, and we sort of manually scan through the buffer to get it. The ESP Ethernet libraries or the ESP Wi-Fi libraries work in a slightly different way for how you specify that. It's a bit cleaner actually, so I do prefer this method, I suppose. What we're going to do here is we use this server.on kind of callback, as it were, and you'll say, so this is the resource that was requested from the server. So a / like this is just kind of like the root home page, the main address, and no specific resource requested. This is when we've requested the /H page, and this is the /L page. And what happens when those resources are requested? Well, if we've gone to the main page, what we're going to do is, again, we're going to look for this P argument. But again, the ESP library provides a slightly neater way of doing this. So we'll say, okay, if the server has got an argument called P, and if the value of that argument is 1, 2, 3, 4, that's when we'll do our toggle, when we turn the relay high and low, and then so the password's entered. And then we'll also call the function that's going to display the HTML back to the browser. If they requested the /H resource, so this is our high one here, so this time we'll turn the relay high and then display the page. Or if they requested the low resource, we'll set it low and then display the page. And you can continue to add more and more conditions like this as you want for as many other pages or extra things. So again, this is what the user is going to type in their browser after the IP address to get to particular resources. And because the ESP has got so much more onboard memory than the Arduino, you can actually create a fully functioning website if you really wanted to, with all sorts of resources and images and forms as well. But for now, we'll just keep these simple examples. Having specified those callbacks, what's going to happen here, we then begin the server, and we'll just put a message to say the server started. Again, we'll put a little bit of delay just to wait for it to stabilize. And then in the loop function, we don't actually have to do anything really. We just continually call this function here, handle client, and that takes care of all of the things that we were having to do manually with the Arduino example. So whereas in the Arduino we were having to check whether a client was connected, whether there is any available data to process, adding it to the ring buffer, searching through the ring buffer. All of that is done within the ESP library for us. When we first set it up, we just specify the behavior that we want to have when certain events happen, and then they will happen automatically when this function is called here. So the ESP is, I think, a neater library to write for and a more capable one as well. But other than that, it essentially works in the same way. Now, I mentioned earlier that there's just a few changes you need to make to your internet gateway as well to allow players who are remote to come in and access your Arduino on your local intranet. By default, most intranets obviously don't allow access from outside. You don't want random people on the other side of the world browsing through your folders when you're online. But in this case, we do want to allow certain connections to certain devices, and that's what we're going to set up here. Now, every router works in a slightly different way. They'll have slightly different screens, but I'm going to go through the web interface for my particular router, which is a Vodafone one. In practice, if you have a small office router or a home router that you're using as well, it will probably have very similar settings. They might be laid out in a slightly different way, but they'll probably use much of the same terminology. So you'll have a similar process to follow. So the first thing I'm going to do is I'm going to go to the settings page, and I'm going to go down to the IPv4 menu here. And what we're going to do here is we're going to assign that static IP address for the device. So if I scroll down here for where we get the static DHCP, you'll see that I've got a number of entries for different devices that are already on my network, and it gives them a name, a MAC address, and an IP address. And what we're going to do here is we're going to create a new entry for our controller, and we're going to specify the MAC address that we used in code. So if you remember from the Arduino code listing earlier, I was using A, B, C, D, E, F, and then 000001 for this particular device. And I requested an IP address of 192.168.1.41. Now, by adding that entry to this table here, what that basically does is it kind of reserves that IP address to make sure it doesn't get assigned to another device that connects to the network. So I'm able to guarantee that the device that uses this MAC address, the one that I programmed in code, will always be assigned this IP address, which is going to make the routing easier. So we'll add that new device there, and we'll click apply. And then having guaranteed that we've got that IP assigned to the particular device we're using, the next thing we want to do is to look at that port mapping issue. So on my router, that comes under the internet option and then port management. And if I just wait for that page to load, you'll see I've already got some ports declared here. So I'm now going to, if we just read there saying port mapping allows remote computers to connect to a specific device within your private network. Well, that's exactly what we want to do in this case. So again, we'll create a new entry in the port mapping table this time. And we're going to create a user-defined service. We'll just call it, so remote escape room control or something like that. And we can either choose a particular device by name if we have an entry in the name table already. You'll see the problem with here is that the names sometimes come up with rather tricky to kind of be certain which one you're actually addressing. So I'm going to go for no specific device, and instead I'm going to use the local IP address that we just entered into the static DHCP table. So we'll go 192.168.1.41, and because we put that entry in the previous table, we know that that's going to always be assigned to the correct device. We'll leave the TCP protocol as it is. That's the protocol that HTTP request uses, TCP, so we'll leave that in. And then we're going to specify a particular port. Now again, if you remember what we defined in the code, we're listening on port 2001. So that's what users will connect to from the public internet, and we'll just map that to 2001 on the local device as well. In theory, you can actually do a kind of a port mapping thing here, so you could have if users requested port 80, which is the default port used for our web server, we could direct them to a port 2001 on this device, but we'll just leave that the same. There's no need in this case to differ there. So we'll save that. And after we apply those changes, those are now everything we need to do to set up the device to be accessed from the public internet. So before, when you're on your local intranet to access this device, we would have to have used the local IP address, which we've got here. And in fact, I can just demonstrate that. So if I load up a new tab and I go to that address, you'll see that we have the escape room controller responding on our local IP address. But now that we've set up these ports, we can also access it over the wide area network, the WAN address, and this is the public IP address that anyone from outside our intranet is going to use. So you see I've actually got it written at the bottom of my configuration page here, but this is also going to be the address that's returned from the ident.me page. So remember, we actually called this from our script earlier. So this is my IP address as I appear on the public internet, which is the same as my router is telling me down here as well. So if I go to there and go to port 2001, I get to exactly the same place as I did on my local network. So this is the IP address that we can give to anyone around the world now, and wherever they are, they can type that in their web browser and they will be able to access our Arduino that is running on our local network here, and by clicking the various buttons here or by entering the password that we specify in the code, they are able to control physical devices here in the room from the other side of the world. So what I've tried to demonstrate in this video is a whole range of options allowing you to expose the functionality of an Arduino controller over the internet and allow players from all over the world to log in remotely and play through your physical escape room games, controlling items such as mag locks via relays or LED displays or linear actuators, or in fact any other tech prop that you'd normally find in an escape room game. They can directly interact with that and see immediate feedback of the effect of their actions via that video streamed link. Now, we are all learning different ways to adapt to this current situation all the time. Game designers are constantly coming up with new ideas, and this is just one approach. I'm really looking forward to seeing the kind of creative innovations that other people are coming up with. But if you do use this approach, or if you have other ideas, do please let me know in the comments. I'd love to see what people are doing out there during this very difficult period. Now, these videos are only made possible with the very generous donations of my Patreon supporters. I want to thank them for that. I know a lot of people are facing difficulties at this time. It's very hard for all of us, so I really want to say very much thank you for your continued support. The code, download, the wiring diagrams, and everything else that supports this project, I will put a link to my GitHub account where you can download those, and I'll also put a link to where I got these components from as well. And all my other escape room projects I've done in the past as well are all available over on my Patreon page. If you would like to, and if you're able to support me, that's amazing and wonderful, but if you can't, especially not during this particular period, absolutely understand, but I'll make these available for download anyway. So hopefully that's given you some ideas. I hope you are well and stay safe wherever you are in the world right now, and I look forward to seeing you next time. Okay, thanks very much for watching.